Hey guys, today I want to present a solution to the Balkan Math Olympiad 2023 problem 1. At first, let's have a look on the problem statement. We are asked to find all functions from the real numbers to the real numbers such that x times f of x plus f of y is equal to y minus x times f of x for all real numbers x and y. A promising idea for this problem is to plug in y equals x, because then our first factor on the right hand side is equal to 0 and therefore our whole right hand side is equal to 0. So let's do this. We want y equals x, and this gives us that x times f of x plus f of x is equal to 0. For x not equal to 0, this directly tells us that f of x plus f of x is equal to 0. This motivates us to prove injectivity of our function, because if we are able to do this, then we know that this argument here must be a constant. So assume that we have f of a is equal to f of b for reals a and b. Taking a look back to our original equation, we see that y is an argument once at the left hand side, and on the right hand side y is only outside of the f's. Therefore, we are motivated to plug in a and b for y into this equation and then use the fact that f of a equals f of b. So let's do this to get that a minus x times f of x is equal to x times f of x plus f of a. Here we can use the fact that f of a equals f of b to get that this is equal to x times f of x plus f of b. And now we use our equation here again for y is equal to b to get that this is equal to b minus x times f of x. This looks really promising, because if we can divide both of the sides by f of x and then add x, we have that a is equal to b, and then injectivity follows. But in order to divide by f of x, this has to be not equal to 0. So at first, let's consider the case that f of x is equal to 0 for all real numbers x. This immediately implies that the right hand side of our functional equation is always equal to 0, and therefore our left hand side is also always equal to 0. So we get that 0 is equal to x times f of x plus f of y. Plugging in x equals to z minus f of y, we get that z minus f of y times f of z is equal to 0. Hence we get that f of z is equal to 0 for all z not equal to f of y. But if we have a look back to the equation that f of x is equal to 0, we also see that if we plug in f of y for z, this is also equal to 0, and therefore this holds for every z. So in this case, f of z equals 0 is our only possible solution, and we can check that this solution indeed works, and therefore we figured out our first solution. Now we are ready to go on with our second case, namely that there exists some x such that f of x is not equal to 0. Using this x in our equation here, we see that we can divide by f of x. Therefore, we get that a minus x is equal to b minus x, and thus a is equal to b, and therefore we know that f is injective. We are ready to go back to our equation that f of x plus f of x is equal to 0 for all x not equal to 0, and therefore by the injectivity of f, we conclude that there exists a constant c in R such that x plus f of x is equal to c for all x not equal to 0. For the case that x is equal to 0, the left hand side in our equation is also equal to 0, and on the right hand side we have y times f of 0. Now, taking y to be equal to 1, we know that f of 0 is equal to 0, and therefore f of 0 must be also equal to c. So this holds for every x. Solving this equation here for f of x, we get that f of x is equal to c minus x for all x, And here we can again plug in this function into our first equation and see that this is indeed a solution. And therefore, we found our second and last solution, and we are done.